Do you know that protons are made up of yet smaller particles? You might have heard of the particle quark, or maybe fermion or boson. Are you confused with what these particles are? What are these new types of particles discovered by scientists in the last 50 years? What is the current understanding in particle physics of what constitutes an atom actually? And where does gravity fit in all of these? Let's try to understand in this video. You must have heard of Large Hadron Collider at CERN lab in Switzerland. What is this Large Hadron Collider? In simple terms, this machine accelerates atomic and subatomic particles to integrate or disintegrate them. With collision experiments of protons, neutrons and electrons in such super colliders, physicists discovered more elementary particles, such as muons, quarks or bosons. Between 1967 and 1975, Steven Weinberg and other physicists put together the standard model of physics to classify the then known elementary particles and the fundamental forces together. Now let's try to understand what this standard model is and what are these fundamental particles. The standard model consists of 12 matter particles called the fermions. These particles obey the Pauli's exclusion principle, where no two particles can occupy the same quantum state. On the other hand, there are 5 force particles also, called as bosons, which do not obey Pauli's exclusion principle. Amongst the 12 fermions, there are 4 sets of particles: electrons, up quarks, down quarks, and neutrinos. Each of these 4 have a group of 3, which makes the total 4 times 3 equal to 12. Let's check the first 3 set of particles: electron, up quark and down quark. Now these cannot be divided further. Now we know that electron has a charge of -1. Similarly, an up quark has a charge of 2 by 3 and a down quark has a charge of -1 by 3. All of the matter that we see around us is made up of these quarks. For example, a proton has 2 up quarks and a down quark, whereas a neutron has 2 down quarks and an up quark. Matter formed from a combination of quarks are known as hadrons. Quarks are never found in isolation, only in combination forms. Also, each quark has an antiquark that differs from the quark only in that some of its properties, such as electric charge, have equal magnitude but opposite sign. The fourth set of fermions are called as neutrinos. Neutrinos are emitted from radioactive decay, example from stars, supernova or atomic reactors. They are called ghost particles as they are hard to detect, having negligible mass and no charge. They don't interact with surrounding matter. Do you know that trillions of neutrinos pass through us every second? Antineutrinos have no charge but different chiralities and other quantum property. As you have seen above, there are 4 sets of fermions. Strangely, fermions come in group of 3. For example, electron, muon and tau. The main difference within a set is the particle's mass. Muon is 200 times that of an electron and tau is 3000 times the size of an electron. These heavier particles are unstable and quickly decay to their elementary particles, in this case electron. Now same goes up with up quark, which has heavier particles called charm quark and top quark, and down quark, which has heavier particles known as strange quark and bottom quark. Now why do these particles come in group of 3 is not known today. In 1968, in SLAC accelerator, these quarks were discovered. The top quark was the last to be discovered in 1995. Now that we have covered matter particles that are called fermions, let's understand where does force come from. As you already know, an electron with a charge of -1 creates an electromagnetic field around it. It repels negative charge and attracts positive charge. It has no effect on neutrinos. This electromagnetic field is made up of photons, a boson particle. So the field that we are used to studying as a wave during our high school years is also a particle, as per duality of nature. Now we have discussed that protons and neutrinos are made up of quarks. What is the force that holds these quarks together? In protons and neutrons, quarks are held together by something known as strong nuclear force. This force is responsible for nuclear fusion in the sun and other stars. It is represented by gluon boson and affects all the quarks. Another force, however, known as weak nuclear force, is responsible for decay of particles into their elementary form. This is the force that is responsible for nuclear fission in atomic bombs. This force is carried by W and Z bosons. So, we have the 4 force particles called bosons for electromagnetic force, strong nuclear force, and 2 for weak nuclear force. But in the start of the video, we mentioned 5 force particles. So which one is the last one? You would remember the buzz around the 5th particle when it was discovered in 2012 from experiments at Large Hadron Collider in Geneva. It was called the God particle by the media and is also known as Higgs boson. The Higgs field is an energy field. When matter particles interact with this field, the potential energy of the field gets transferred as mass of the particle. The higher a particle interacts with the field, the higher is its mass. So, this particle is also said to give mass to almost all the matter around us. Why almost though? Because not all mass is generated from Higgs field. For example, 99% mass of protons come from kinetic energy of the quarks and energy of gluons. Gluon, as we have discussed before, is the particle responsible for transmitting strong nuclear force. However, scientists do feel that Higgs field may be responsible for mass of all the dark matter. So to summarize, the standard model consists of 12 matter particles called fermions and 5 force particles including the Higgs boson, the God particle. So is this the final model? Sadly no. The standard model is also not complete. You would have noticed that it is unable to include the fundamental force of gravity. As you know, Newton and Einstein used gravity to describe interactions between stars, planets, and everyday objects on Earth. It is a macroscopic field calculated using general relativity. However, quantum physics has not been able to incorporate it for microscopic particles. During his last days, Einstein tried to create a theory of everything which could include both gravity and quantum physics together. Now, another issue with standard model is that it only comprises matter particles in our knowable universe. It leaves out 95% of the universe, which comprises of dark matter and dark energy. Scientists are yet to understand what dark matter and dark energy constitute of. So to summarize, there is a lot to be discovered in particle physics. If you liked the above video, let us know in the comments what other topics interest you. Also, please like, share and subscribe to our channel, Just.